Hello, my name is Kaylin Ebener, and this is my lab on constant velocity. In my presentation, I will be discussing how I performed a real-life observation of constant velocity, created a computer model of the system, compared my real-life observation to the computer model, and then I will discuss the physics principles involved. There were several goals in this lab, the first of which was to implement Newton's second law, which states that the net force is equal to the change in momentum divided by the change in time. We used Newton's second law to create the position update formula and velocity update formula that allows us to model the motion of the object in a program called GlowScript, which used Python code. Before we could create our program in GlowScript, we first had to analyze a video and tracker to obtain the initial position and initial velocity of the object, which are both values needed to create our computer model in GlowScript. I recorded a standard basketball motion, which has a diameter of approximately 0.24 meters and a mass of approximately 0.624 kilograms. This data was used to calibrate the motion in tracker and initialize the computer model in GlowScript. I recorded the basketball motion on a driveway, which was a hard surface, to hopefully minimize the force of friction. Here is the video of the basketball moving in the negative x direction. There are multiple key features in tracker, one of which is the orientation of the axes set for the ball moving in the negative x direction, which is reflected in the graph of motion here. The calibration stick is set to the diameter of the basketball to optimize realistic conditions, and right here. And down here is the table of times and position points of the basketball as it moves. The initial position was taken straight from the table, and the initial velocity was calculated using the difference of the first two position points over the time, and these values were used to initialize the GlowScript program model of motion. If my axis orientation was changed from negative to positive, which is shown in the graph as the purple arrow to the peach arrow, the magnitude of the vectors would remain the same, which is shown by the magnitude formula. However, the direction would change. This would flip the slope of the position versus time graph, and it would flip the sign of the velocity. To initialize my GlowScript program, I input the basketball's mass, the initial position, the initial velocity, and the change in time from my tracker program. I input net force to be the zero vector due to there being no net force on the system. This is proven because there's constant velocity, so the initial velocity is equal to the final velocity, deeming the change in momentum to be zero. Since net force is equal to the change in momentum over change in time, then the net force is equal to zero, which I accounted for in the GlowScript program through this line of code circled below. So this is the GlowScript program running. Here's my code. Next, you'll see the model running, and as you can see, the object is moving in the negative x direction. Below is the position versus time graph, which has a negative slope, as expected, right here. And next is the velocity versus time graph showing constant velocity. Below there, the numbers are the position and time data that the model produced. I created my comparison with the time and position data from Tracker and GlowScript put into one graph. This line graph was created in Google Sheets with the data. You can see that there was some divergence here, and this could have been due to the presence of outside forces slowing down the ball, even though precautions were taken to minimize the effect of outside forces. The irregularities could have also been due to a shaky hand when filming the video, skewing the frame, or the video blurring the center mass so it cannot be placed accurately. There are multiple ways that this model could be improved. In terms of the real-life scenario, another surface could be used to minimize friction and eliminate any irregularities in the object's path that would cause it to veer off course. Concerning tracker, a better camera with more frames per second could have been used, or more decimal places and position values could have been incorporated for more accurate position data. To improve the computer model, forces that affect the object in real life, such as drag and friction, could have been included in the calculation of net force, affecting the movement of the object in the model and making it more realistic. In describing the motion, we utilized a net force of zero. However, the net force is a summation of many other forces such as gravity, drag, normal, and friction forces. For simplicity's sake, in our model, these other forces are not included, and we could not determine how many forces were acting on the object. The absence of them keeps us from having a perfect model in GlowScript, but it must be noted that in real-life scenarios, these forces come into play. In this lab, we learned how to use Newton's second law, that the net force is equal to the change in momentum over the change in time, and we used the velocity and position update formulas with constant velocity causing the net force to be zero. This lab was a study of an object with constant velocity, and that allowed us to create a simple model of this motion. That's all. Thank you for your time.